Everyone. So welcome to the lecture series of CMOS by KT Semicon. Okay. So in previous session we'll discuss the things related to semiconductor physics, right? So why silicon? Why only we use silicon for manufacturing chips and all, and what is made by N-type semiconductors and P-type semiconductor, and differences between intrinsic semiconductors, extrinsic semiconductors, and all the things, right? So in today's session we'll discuss the things related to MOS technologies, which means we are having MOS capacitors and MOSFETs, right? And all these things we'll explain. And for a MOS capacitor, the MOS capacitor is working on four different cases. So I'll explain all those things in today's lecture. Okay. So let me share my screen. Yes, I hope my screen is visible, right? So in today's lecture, we will discuss the things related to CMOS capacitor. So, MOS means metal oxide and silicon, right? So, SiO2. So, here this is the one of the layer, and this is the layer, and this is the one of the layer. Okay, we'll discuss complete things. Okay, so first one is for a particular capacitor, MOS capacitor, we are having three different layers. Okay, first one is metal layer. Okay, metal. This metal is acting as the gate. Okay, this is going to act as a gate. And the second one is oxide. Sorry. So second layer is oxide. This is going to be work as the insulator. Okay, in between gate and substrate. And the third one is substrate. Okay, so either it is N type or P type. Okay, so this is the thing. And MOS capacitor, this is the foundation of MOSFET. So if MOSFET is in one of the transistor, right? Every transistor having this MOS capacitor. Okay, so some basics of MOS capacitor. MOS capacitor consists of a metal oxide semiconductor layer structure. So see here. So this is the one of the layer, and this is the another layer, and this is the another layer. This layer is going to be access the metal, and here we connected gate terminal. Here this is my gate terminal, and here I'm choosing P-type substrate. Okay, and here we are having one layer SiO2. Okay, silicon dioxide. This is acting as the insulator. Okay, insulator. Here, these are the three things. It forms a voltage dependent capacitor. What is mean by voltage dependent capacitor means whenever we are applying the voltage, then only it will start working. So here we are connecting some voltage. So from gate terminal to substrate terminal. So here we are applying some voltage. Whenever we are applying the voltage to this gate terminal, then only this MOS capacitor will start working. Okay, so as compared to BJTs, so before MOSFETs and MOS capacitors, we are having BJTs also, bipolar junction transistors. So what is the drawback of this bipolar junction transistors means it will consume more power. Why? Because BJTs are completely working under current, right? It is a current controlled device. That's why it consumes more power, right? So it occupies less space, so it is more suitable for integrated circuits. Okay, so as compared to BJTs, it will occupy less space, which will my MOS capacitors will occupy less space as compared to BJTs, so it is more suitable for ICs. So we need to do as much as minimize the ICs, right? So that's why we are moving from BJTs to MOS. Okay, so MOS capacitor is not widely used in devices, but MOS capacitor is present. See, so MOS capacitor is only the thing we are not use it widely, but include MOS capacitors are including in MOS transistors. Okay, MOS transistors means MOSFETs. Okay, so we cannot widely use it only MOS capacitors only. We can MOS capacitors are in there in that MOS transistors. Okay, we're using this MOS transistors. Okay, for constructions and all. This is the main agenda of MOS capacitor. Okay, so some basic things of MOS capacitor: metal or polysilicon material used in the metal layer. So in this 1 minute I erase. So so metal or polysilicon material is used in the metal layer. So here this is my first layer, right? So this is my metal layer. To that metal layer, we're connecting the gate. Either we can select either metal or polysilicon. Okay, and the SiO2 layer is acting like a dielectric layer. Okay, so here this layer is acting as the dielectric layer. Why? Because this is acting as the insulator, right? Insulator means it cannot allow any kind of electrons in it. Whether we are increasing the temperature also, it won't allow any kind of electrons in it. At that time it will give some electric fields in this oxide layer. Okay, so that's why it is acting as the dielectric layer. Okay, so this forms a capacitor in between the gate and substrate. Okay, this acting as the capacitance in between my substrate and metal whenever we are applying the voltage at the gate. Okay, so this p substrate is trying to attract the gate. Okay, so in that process here my oxide layer is insulator, right? That's why it won't allow any kind of electrons to passing through this oxide to this metal. So that's why it acting as the dielectric medium in between the metal and p substrate. Okay, so the thickness is there in order to 10 nanometer to the 50 nanometer. This is the thickness of the what SiO2 layer. So in semiconductors, p-type and n-type semiconductor is used. So while selecting this substrate, either it may be n-type or else p-type. We can select whatever we want depending on the construction of the transistor. Okay, so this is the thing. The capacitance of the MOS capacitor depends on the voltage applied at the gate terminal. Okay, so I'll explain you, right. This is my gate. Okay, VG means gate voltage. So whenever we are applying the VG voltage, then only my MOS capacitor will start working. Okay, so this is the thing happening here, and usually the body substrate or base is grounded when the gate voltage is applied. So whenever we are applying the voltage here, okay, so whenever we are applying the voltage, okay, see here, this is connected to the ground. This substrate terminal is connected to the ground. Okay, so for every electronic device we are connecting one terminal to the voltage, which means VDD, right, and the another terminal we are connecting to the ground, which means VSS, right? Correct. So this is the thing happening here. This is the complete some basic points of MOS capacitor. Clear? So after that we are having some energy band diagrams of P substrate. So for before going to do energy band diagrams, we need to clear about covalent bond and valency bonds, conduction band and valency band, right? So this is my valency band and my this is my conduction band. Okay. So actually in valency band is fully packed with electrons, right? So my valency band is fully packed with electrons. Okay, so whenever we are increasing the temperature, okay, then my electrons in the valency band starts jumping from valency band to conduction band. Correct. So this is the thing happening here, right? So whenever my electrons is jump to that conduction band, then what will do? Electrons are freely move in this band and they'll conduct some current, right? And then current will be increases. So this is the thing happening here. So here we are having conduction band, okay, and here valency band. So whenever the gap between the valency band and conduction band is known as band gap, right? The energy is required to jump from my valency band to conduction band is known as the band gap, right? So here this is the thing happening here. This is the p type substrate. So in p type substrate mostly majority carriers or holes. Okay, 50% of the, so here fermi level is the 50% probability of either holes or electrons, right? So p substrate is mostly contains holes, right? So after moving from electrons valency band to conduction band, then what happened? It will leave some holes in the valency band. Okay, while jumping this electrons from moving the electrons from valency band to conduction band, then it will leave holes in the valency band, right? That's why we are having more holes in the valency band now. Then what happened? 50% of the probability of holes is there in valency band. That's why my Fermi level is near to this valency band. Clear? This is the thing. And so intrinsic Fermi level, here my intrinsic Fermi level is exactly in between my valency band and conduction band. Why? Because for intrinsic type we are having equal number of electrons and holes, right? That's why my intrinsic Fermi level is exactly is there between my conduction band and valence band. So here we are having another thing like free space, right? So whenever my electrons are crossing this conduction band, then my electrons are completely free in the nature. Okay, so this is the thing. The conduction band is between the band gap in between conduction band and valency band is 1.1 electron volts. So this is the energy to energy required to move a electron from valency band to conduction band. Okay, so this is known as band gap, right? This is known as band gap. So Fermi potential phi f is based on intrinsic level. Okay, so by using this intrinsic Fermi level we can find the Fermi potential also. Fermi potential, okay, this is the thing. And after that, energy band diagram of a MOS capacitor. So usually MOS capacitor contains three layers: metal, oxide and semiconductor, right? So for metals, what happened, my valency band and conduction band are here. We are having conduction band and we are here we are having valency band, right? What happened to the metals? For metals, there is no band gap in between my valency band and conduction band, right? There is no space. So here also there is no space in between, there is no space in between my valency band and conduction band. So check here, oxide. Oxide means here oxide is acts as the insulator, right? So that's why we are having this much of band gap in between my valency band and conduction band. We are having more space, more band gap. Understand? So why? Because here my oxide is acting as the insulator, right? So for semiconductors, so here for semiconductor, this is the we are selecting P type, right? P type substrate. That's why my Fermi level is near to the valency band, and here we are having, as compared to oxide, we are having less band gap. Okay, so this is the thing, and after that we are having conduction band. Okay, and this is the Fermi potential. Okay, so this is the thing as compared to three layers. After that, we are having one energy band diagram of combined MOS structure. So this is the energy band diagram. Okay. So when we combine the three MOS metal layers, Fermi level must line it up in a single line and free space must be continuous. So here, check it here, my Fermi level is same. Okay. For all the, we are combining all the three layers. For three layers, my Fermi level is same. And the, what is the main difference? The distance between the, which means band gap, right? So here this is the free space and this is the conduction band and intrinsic level and valence band. Why this curve happened means I'll explain. Okay, so here we can observe one curve like structure, right? So because of we are selecting P substrate, it will came into the picture. I'll explain. Because of work function difference in between semiconductor and metal, there is a voltage drop across MOS and banding of bending of bands. I'll explain why this bending is happening and all. Okay. So for ideal MOS capacitor, what is meant by ideal MOS capacitor? Ideal MOS capacitor, we are giving some voltage as zero. Okay. So these are the some of the assumptions. Okay. Work function of metal and semiconductors are same because in semiconductor also, okay, semiconductor also acting as the insulator, right? When at the 0 degrees Kelvin. Okay, so that's why here work function is same for metal and semiconductor. The oxide layer has no charge. Okay, it has an ideal insulator. Here we are not applying any voltage, that's why there is no electric field, dielectric medium in the oxide layer. Also the oxide layer has infinite resistivity, so it is having more resistivity. Okay, so no surface states of at the oxide and the semiconductor interface. Okay, so this is the thing happening here. No surface states means, so whenever we are applying the voltages, then applying the positive voltage or negative voltage, we can see one layer in between oxide and semiconductor interface in between both of them. So here we are applying zero voltage at the gate, which means ideal case there is no voltage. There is no voltage means there is no operation in this capacitor. So at this time there is no surface state at this space in between the oxide and the semiconductor interface. Understand? So this is the thing happening here. So after that we are having four different kinds of cases. Okay, first one is flat band. So how flat band is created? So when we are applying the gate voltage as zero, Okay, these are the four different cases. I'll explain each and every case. Okay, so after that, whenever we are applying the gate voltage as 0, then we can find this flat band region. After that, we are applying some VG voltage is less than my 0, which means we are applying some gate voltage is negative voltage. Okay, so when we are applying gate voltage as 0, then we can see the accumulation region. Okay, in the MOS capacitor. After that, we are applying the positive voltage. That positive voltage is small amount of positive voltage. Okay, so we are applying small amount of positive voltage at the gate. We can observe some depletion region. Okay, so after that, we are having inversion region also. Inversion region means my positive voltage here we are applying some positive voltage, right? So now positive voltage is more than my threshold voltage. Okay, so at that time we can see some inversion region. Okay, I'll explain all the things here. So first one is flat band region. So wait, I'll explain, I'll draw and explain. Okay, so this is my metal and this is my oxide and this is the p substrate, p type, right? P substrate. Okay, so here this is my VG. Okay, so first thing we are applying here 0 voltage. Okay, so whenever we are applying the gate voltage here in P substrate, my majority carriers are holes, right? So here we are having some majority carriers holes. Okay, so this is the thing. So here when we are applying the gate voltage as 0, so in the first slide I'll explain one point, right? MOS capacitor is dependent on applying gate voltage, right? So here we are not applying any kind of voltage. Here we are giving the voltage as 0. At the time, no operation is occur in this MOS capacitor, which means there is no band bending also in this region. The energy bands of the semiconductors are completely flat. Why completely flat means there is no operation in this MOS capacitor. Okay, if we applying any either positive voltage or negative voltage, then we can see the differences in the energy bands. Okay, but we are not getting any kind of bands by because we are applying 0 voltage. Okay, so there is no curvature or distortion in the bands. Okay, charge neutrality, because the bands are flat, there is no depletion region and no excess charge at the semiconductor surface. Whenever we are applying the voltage, then only my MOS capacitor starts working. Here we are applying 0 voltage, right? That is why there is no operation and there is no depletion region also. Okay, and now work function also same. Okay, there is no variation also. So this is the thing happening here. So Fermi level is both for all the things, and this is the flat band region. There is no bending here, right? We can see there is no bending of the bands here. Okay, so for p-type semiconductor my bands are usually like this, right? But here we can not, here all my bands are in flat. Okay, so this is the thing. And after that we are applying some gate voltage as negative voltage. Okay, so again this is my metal, this is my oxide, and my this is my p substrate. Okay, so here this is the gate VG voltage, and here we are connecting the substrate to the ground. Okay, so now at the gate we are applying some negative voltage. Okay, so here we are applying some negative voltage, understand? So at the gate we are applying some negative voltage. See, in my substrate I am having majority of what? One major p-type substrate, majority carriers are correct holes, right? So holes means positive charge. So what happened now? Whenever we are applying the gate voltage as negative, then this p-type substrate having positive voltage, right? So this positive voltage is try to attract this negative voltage. Then what happened? All the holes in the p substrate, okay, try to move from the, try to attract to the gate. Okay, so it will try to attract the gate, and because of the dielectric, because of this oxide layer. Okay, this oxide layer is acts as the insulator, right? So this oxide layer won't allow any kind of charges through this insulator, right? That's why all my holes with positive charge are accumulated at the surface of the substrate, which means near to that oxide layer. So what happened here? We are getting one accumulation of holes region here, right? This is the accumulation of holes. Okay, whenever we are applying the negative voltage, so the substrate contains positive charge, right? So this positive charge is attracts to the negative charge. Okay, so because of this dielectric medium, which means because of this insulating layer, it won't allow these charges. That's why there is a formation of accumulation of holes in the near holes on the substrate top layer, okay, which is near to oxide layer. Okay, so in this case, my electric field, so there is a formation of electric field in this insulator, right? So my electric field is in the direction of electric field of the oxide layer. Okay, always electric field is traveling from positive to negative direction. That's why my electric field in the direction through towards the gate. Understand? So accumulation occurs typically for negative voltage. Okay, where the negative charge on the gate attracts holes from the substrate to the oxide semiconductor interface. Okay, understand? So whenever we are applying the negative voltage at the gate, these holes in the positive charge in the p substrate, it's try to attract to the gate. Depletion layers occur for positive layer. Okay, so here we can see one layer. Okay, this is the accumulation of holes, right? So this is the thing, and electric field is directed towards gate. So electric field always trying from positive to negative. So here positive voltage is in the p substrate and negative voltage is gate, right? That's why my direction of electric field towards the gate, and neither holes nor electrons can cross the oxide layer. Neither means it won't allow holes or electrons, right? That's why we can get accumulation of holes here. Understand? So after that, this is the energy band diagram. Okay, so this is the metal. So assume this. Okay, this is the diagram. Okay, there is no line here. Okay, this is the diagram. So we are having more electric field. So this is the line for electric field. Okay, so my electric field is more at the gate, right? Gate means metal. So this is the metal, right? So here this is the metal. So we are having more electric field at the gate as compared to substrate, right? So my electric field direction is in their form. Okay, so the slope indicates the electric field. We are having less value at the semiconductor substrate, and we are having more electric field at the metal. So this is the thing, and after that we can see some bending in the, some bending happens, right? This bending is happens because of accumulation of holes. Okay, so there is a space is occupying here because of the holes. Okay, there is accumulation of holes here, right? See here, there is accumulation of holes whenever we are applying the negative voltage. Okay, so this is 0. Okay, so here this bending happens. Why? Because there is accumulation of holes. Okay, so even though my substrate is p substrate, right? That's why my Fermi level is near to the valence band. Okay, this is the thing happening here. So after that, what we are doing, we are applying the positive voltage, small amount of positive voltage. Okay, now what happened? So again, this is my metal and this is my oxide. Okay, this is my p substrate. Okay, so at the gate, okay, we are applying the gate voltage as positive voltage, that is the small amount of positive voltage. Okay, so whenever we are applying the positive voltage at the gate, okay, what happened now? My majority carriers are holes, which means positive charge. So because of this positive charge, my holes will repel. Why? Because same charge will repel, right? So here also we are applying positive voltage. That's why my p substrate also consisting holes consisting positive charge, right? That's why it will repel, and holes will try to move into the deeper into the substrate. Here we are having source, right? So this holes try to go deeper into the substrate because of this repulsion forces. Okay, these holes will try to deeper into the substrate and it will leave one negative electron. Okay, negative ion. So whenever hole is moving from one here to the deeper to the substrate, okay, then it will leave one negative ion. So what happened now? So whenever we are applying the positive voltage at the gate, so these negative ions are try to attract this positive voltage. Okay, so whenever my holes are moving deeper into the substrate, then it will leave one negative ion. Okay, so because of this positive voltage the gate, these negative ions are try to attract this positive voltage. Okay, then what happened? These negative ions forms a layer at the surface of the substrate and O2. Okay, oxide layer. So now what happened? We can see one depletion layer here, right? So this depletion layer is fully filled with negative ions. Okay, so now what happened? My depletion region is formed at the surface. So holes repelled. Why? Because positive gate voltage pushes holes away from the interface. Okay, because of the repulsion forces my holes are get deeper into the substrate and it will leave one ions. So fixed ion left, mobile holes leaves exposing fixed negative acceptor ions. Okay, it will leave one acceptor ions. Depletion layer forms. A region divided of mobile carriers phase charge region is created. So because of these negative ions, so these negative ions are trying to attract this positive voltage and it will create one depletion region. So energy band bends upward in the interface. Why it is bending upward means that space is filled with, here space is filled with electrons, right? So before that we are having holes. Holes means space, creation of space. So that's why here space is created. But now see, so here check here. So this is okay, so check here. So it will create depletion layer is fully with electrons. Okay, so here is zero. Okay, not voltage. So whenever we are applying the positive voltage at the gate, there is a formation of depletion layer with negative ions. Okay, which means electrons. Now it is filled with electrons. That's why we are having up, we are having bending in the upward direction. So before that my bending is downward because space is created. Now what happened? We are filling that space with electrons, right? That's why my bending will happen like this. Okay, so this is the thing. And here also my, see, now my electric field is in the direction towards the substrate because from positive to negative side, right? So here we are having electric field, right? So my electric field in the direction from gate to the substrate, positive to negative. That's why we are having less at the metal and more at the gate. Okay, so my electric field is in the direction of here to here, positive to negative. Okay, so this is the thing happening here. Okay, so this is the energy band diagram of a depletion region. Okay, so after that we are applying the gate voltage is more than my threshold voltage. So up to now we are applying only small amount of positive voltage. Now what happened? We are increasing the amount of positive voltage. That positive voltage is more than my threshold voltage. See, now what happened? So up to now we are having only negative ions, that too small amount of negative ions. Why? Because we are applying only less. So now we are applying more threshold voltage. Okay, so my gate voltage is more than threshold voltage and then we are applying more positive voltage at the gate. Okay, my electric field direction is same from metal to, from gate to the substrate. Now what happened? So whenever we are increasing the voltage is more than my threshold voltage, then what happened? My p substrate, in the p substrate majority carriers or holes, right? All the holes or go deeper into the p substrate. Okay, all the holes. Okay, so in before in this case it will only few amount of holes are moving into the p substrate. Okay, deeper into the p substrate. Now we are increasing the voltage, right? So at the time what happened? The all the holes present in the p substrate are go deeper into the substrate and it will leave one negative ions. So now my complete substrate is filled completely filled with negative ions. Okay, so before that only small amount of layer, now completely filled with negative ions. So completely filled with negative ions means electrons. Now it starting acts as the n type substrate. Okay, so that is the reason behind inversion. Now what happened, actually p substrate is holes filled with positive charge, but applying the voltage at the gate, more voltage, that voltage is more than my threshold voltage. Okay, what happened, my complete substrate is trying to acting as the n type, because all the substrate is now packed with negative ions, right? So this is the thing happening here. So which means inversion layer, which means inverted, right? From positive to negative, it is completely inverted. Okay, so my electric field direction is same. Okay, electric field is direction towards the substrate. Okay, so this is the thing happening here. See, before that we are having a bend up to here, we are having only small amount of bend. Okay, whenever we are increasing the voltage, there is a more occupation of electrons. Okay, negative ion, that's why my bend also increases. Okay, here bending also increases, right? So this is the known as inversion region. Okay, so that is the thing completely related to four the cases. Okay, so flat band region, accumulation region, depletion and inversion. So these are the four cases of MOS capacitor. So that's it guys, thank you.